Thank you for the introduction. Thank you for coming here for my talk. I will show you how we prove the exotic structures using transfer reactions using beryllium isotope as examples. So this is the outline for my talk. Firstly, I will show you some overreaching questions of nuclear physics and the transfer reaction as a tool to study the evolution of shells and the nuclear effective interactions. And using the fluorine example, I will show you how we study the nuclear effective interactions using one-nucleon transfer reactions. And using beryllium 11 negative parity states and the beryllium 12 intruder states, I will show you how we study the exotic structure of nuclear using one-nucleon transfer reactions. And I will show you how the coupling to continuum effect have an influence on the resonances of beryllium 12. Finally, I will show you some new science opportunities with reaccelerated beam coupled to ATTBC and Solaris. So probing the nuclear force in the weak bonding system is a topic of high priority in the current nuclear structure research. It is well known that the single particle excitations involve at a number of nucleus. So tracking this evolution serves as an important approach to study the nuclear interactions. Throughout the chart of nuclear, as I show here, the shell gap changes have been found all throughout the chart. So it's very important to track this change in order to map out the mechanics driven behind. So deducing the effective interactions from the experimental data is a key to understanding the shell evolution and to improve the shell model calculation. So these interactions can be applied in the configuration interaction calculation, which can give refined spectrum. So nuclei with 1 and 2 nuclei away from the closed shell can be used to derive the effective interaction and its corresponding matrix element. This was inspired by the Schaefer-2 method in this paper. And as I show here, for the out nuclear, the out proton and out neutron can couple with each other. So this will result in many different multiplets with different G values. The single particle strengths within these multiplets can mix with each other. So in order to study the effective interaction, it's very important to isolate the single particle strengths. So a question is how we can isolate them. So transfer reaction provide a great experimental tool to study the shell evolution as well as the effective interaction. As I show here, the angular distribution determines the angular momentum of the transferred nuclei, and the single particle and the single particle spectroscopy factors can be determined by comparing to the calculation like a DWBA calculation. And we can determine the single particle energies by the weighted average of the spectroscopy factors timing the excitation energies, as I show here. So therefore, you can see that using one-nuclear transfer reactions, we can isolate the different single particle strength. So it is well known that the single neutron iodine reaction probe the vortices of the orbital, and the single neutron removal reactions probe the occupancies of the orbital. So as I show here, you can see that in the nickel isotope, we can probe the vortices and occupancies of the orbital using one-nucleon transfer reactions. So based on this basic principle, we can define the quenching factor of one-nuclear transfer reactions. So in this paper, using the consistent optical model parameters, constant value of the quenching factor can be obtained from 0.4 to 0.7. in one experiment, we can measure most of the single particle strengths within one orbital. Then, using the corresponding vacancy or occupancy of the orbital, we can normalize, using the sum rule, we can normalize the spectroscopy factors. So in this way, we get the relative spectroscopy factors. This will reduce the uncertainty from the optical model parameters and also uncertainties from the absolute cross sections. So that's why we prefer to use the relative spectroscopy factors rather than the absolute values. So the transfer reaction can be carried out using normal or inverse kinematics. Usually the normal kinematics are carried out using a spectrometer, which can give very good resolution, as good as 10 keV. So the inverse kinematics open opportunities for the study on the rare beams, but the resolution can be worse due to the beam quality and also the kinematic compression at the forward center of mass angle for the inverse kinematics. So here I show you some famous equipment all around the world, which were designed to carry out the measurement using for the one nuclear transfer reaction in inverse kinematics. So another well-known equipment, Helios, has overcome the kinematic compression by applying the magnetic field. This equipment has been used in some of the work I will show you later. So after summarizing some basic ideas for the one nuclear transfer reactions, I will, using the fluorine 22 example, I will show you how we approach the nuclear effective interactions using one nuclear transfer reactions. So these fluorine 21BP reactions were carried out in using Helios with the silicon array upstream of the target. So the protons at the backward laboratory angle were banned by the magnetic field and detected by the silicon array at the upstream of the target. And from the E versus Z spectrum, the projection of this spectrum gives the excitation energy spectrum of fluorine 22. And gated on different excitation states, we can determine the cross sections, and also by comparing with the DWBA calculation, we can get the corresponding angular momentum and the spectroscopy factors in each state. So as I said before, we can use the weighted average of the SD shell orbital. We can using the weighted average of the spectroscopy factors, we can determine the single particle energies of the SD shell orbital. And then we can determine the n equal 14 and n equal 16 shell gap in fluorine 22. And by comparing with the shell model using different interactions, we can see that how the USD interaction underestimate the D3 half single particle energies compared to the experiment. So that's how we can test the different theoretical models. And using this method, we can apply the one nuclear transfer reactions on more exotic beam in the future facility like IFRIB. So also we can, based on what I discussed before, we can deduce the nuclear effective interactions using this nuclear close to the closed shell, and also deduce its corresponding matrix element. So this is not the focus of the present talk. So I will go to the next topic, and you can find the more detail in this paper. So in the light nuclear, there is many examples with exotic structures like halo nuclear, boron nuclear, three-body system, and shell intruder states. Here I show you some nuclear with halo structure, and for the two-neutron halo nuclear, they have very strong three-body structure. And for some nuclear, although they do not have a halo, but they still show very strong three-body structure. Like beryllium 12 and beryllium 14, so they show strong structure with the two valence nuclear coupled to the core. So in for some nuclear close to these regions, their ground state is a resonance. So here I show you one figure I get from Simin Wang. So here I show the very important region around beryllium and lithium. You can find all these different exotic structure in this region. And the unbound ground state of lithium-10 was suggested to contribute greatly to the structure of lithium-11. Which is a two-neutron halo nuclear. So we expect the same thing happen to beryllium-11 and beryllium-12. So the beryllium isotope provide a great testing ground for many nuclear models. The small number of valence neutrons allows the study within the ab initio method, and also it allows for test with the single particle structure within the shell model. And also there are some indications for the cluster structure within this isotopic chain. So there we can test the cluster model with their structures, and the deformation degree of freedom allows the test within the Nielsen model. So as I show here, you can see how the structure within this isotopic chain varies with each other with different mass number. So in the following part, I will show you how we study these structures of beryllium isotopic chain. Firstly, I will show you how we test the different theoretical models using beryllium-11 negative parity state. So beryllium-11 is well known as a halo nuclear with a weakly bound neutron coupled to the beryllium-10 core. So it has an unusual ground state of 1/2 plus, which is inverted with respect to the first excited states 1/2 minus compared to the conventional shell model. So boron 12 has one more proton in the p3½ orbital. So this, but the boron 12 has a ground state has a spin parity of 1 plus. Most studies show that the ground state of boron 12 is dominated with the configuration within the p shell. So if using the d helium-3, we can remove one proton from the p3½ orbital, we will be strongly populate the configuration of the negative parity states within the p shell. So some negative parity states, they have some two neutron excited to SD shell. This won't be strongly populated. So this measurement was also carried out using Helios, but with the silicon array downstream of the target. So I already showed you how we did the analysis for this kind of reactions. So I will directly show you our result and how we compare with the different models. So we compare our result with the shell model, a Nielsen model, and the ab initio approach. And you can see here, this is the experimentally determined spectroscopy factors for the low-lying negative parity states. And although we can't separate these two states, but we can still use the sum of the spectroscopy factors from the theoretical calculation to compare to our result. And as you can see here, the shell model calculation can correctly predict the spectroscopy factors compared to the experiment. But the level order of these two states, 3½ minus and 5½ minus, are inverted compared to the experiment. Compared to the VMC model calculation, we can see that it gave a corrected level order, but there are much more mixing between these 3½ minor states. So, and also we compare our result with Nielsen model. With a strong coupling picture, we determine the spectroscopy factors, but these two are relatively smaller than the experiment. So this indicates boron 12 is not a strong coupling picture. So the calculation within the decoupling scheme is still under investigation. So after looking at beryllium 11, the immediately question goes into beryllium 12 with 1 more neutron outside the beryllium 10 core. So the question is, what is the single particle configurations of the low-lying state of beryllium 12? Now, using beryllium 12 intruder state, I will show you how we study the single particle configuration mixing within the 2,0+ state of beryllium 12. So beryllium 12 has 4 particle bound states. The lower energy of the 3 excited states indicate the breakdown of n equals 8 magic number. So in the excited state, there is also an isomeric state with a lifetime of around 300 nanoseconds, which decay will a very large decay branching ratio will emission of electron pairs. So for these 2 states, the ground state and the isomeric states, using the configuration mixing theory, we can write their wave functions in the following format, with the last 2 neutrons outside the beryllium 10 core occupy the S1/2, D5/2, or P1/2 orbital. So here I summarize some experiment and theory calculations for these 2 states. You can see that how they varies with each other for the single particle component within these two states. And although most of them agree with the dominant SD shell intruder in the ground state, but the relative intensity of the S and D are still not in agreement with each other. So we carry out the beryllium 11 DP reactions at RCNT Osaka University to selectively populate the ice wave component within these 2 0+ states. So we use the annular silicon detector at the backward angle to detect the proton from the DP reaction. And we use the 0-degree telescope to detect and identify the beryllium isotopes as a coincidence method. And also, in order to identify these isomeric states, the 0+ states, we use the scintillator detector to surround the 0-degree telescope and detect the gamma ray decaying from these isomeric states in order to separate from other excited states. So gated on the protons at the backward angle, we can get the particle identification spectrum from the 0-degree telescope. We can identify the beryllium isotopes quite well. And then gated on the beryllium 12, we can get from the kinematics of the protons on the annular silicon detector, we can get the excitation energy spectrum. And gated on the ground state, we get its cross sections. And for the second 0 plus states, we use the triple coincidence of beryllium-12 protons and also the gamma ray decaying from these states to get its cross sections. So after getting these cross sections, by comparing with ADWA calculation from Dan Pang, we can determine the ratio of spectroscopy factors of these two states to represent the ratio of ice wave component within these two states. We use the ratio of these spectroscopy factors because it has more stability using different optical model parameters. So after we get this ratio, we using the configuration mixing theory together with the orthogonal and normalization condition, we can get the single particle component within these two 0 plus states, the S wave component and the D wave component here. So also we can deduce the quenching factor for this measurement, which is also within the previous reported range. So now we get the single particle component within these two states, and then we can compare with the theoretical calculations. So we carry out the shell model calculation using the Weissox interaction from Chen-Xi Yuan, and we can see that compared with the experiment, this calculation result underestimate the D wave component for the ground state and the P wave component for the isomeric states. So we lower the D5½ single particle energies by 0.5 MeV. This gives a much better agreement with the experiment. So we can say that from our result, the ground state of beryllium-12 is dominated with D wave intruder configurations. So this is a dramatic change from compared to beryllium-11, where the ground state is dominated with ice wave configurations. This is possibly due to the stronger pairing in the D5½ orbital, where the two neutrons outside the beryllium-10 core prefer to occupy the D5½ orbital, and also possibly the deformation degree of freedom lower the D5½ single particle energies. This has been observed in the level scheme of Nielsen model. So we can also compare the experimental level order to the theoretical calculated one. We can see that with the lower of the D5½ orbital, the level order of second 0 plus state and 2 plus states also is corrected compared to the experiment. But we can still that the excitation energy of these excited states are still overestimated by the shell model. So this indicates there is still something missing in the shell model calculation, especially for this weak bound 1- states. So possibly we cannot include the coupling to continuum effect in this shell model. So in order to look into this effect, we will look at the unbound states or resonance of beryllium-12. So now I come to this part. I will show you how we how the coupling to continuum effect have an influence on the beryllium-12 resonances. So from the Deer degree telescope, we can see that there are some beryllium 11 and beryllium 10 events, which probably corresponds to the unbound states of beryllium 12, which decay via emission of 1 and 2 neutrons. So gated on beryllium 11, we see the excited states decay via emission of 1 neutron, and there are at least 2 or 3 states populated here. Although this is just some preliminary result. And for these 2 states, they have a very small branching ratio to decay via emission of 2 neutrons, because there is barely any events corresponds to coincidence of beryllium 10. And one state or at here is just about the 1 neutron saturation energy. The other states is about the 2 neutron saturation energy, but have a very large decay branching ratio with emission of 1 neutron. So in order to validate the existence of these 2 states, we look at the spectrum at a different laboratory angle, and these 2 states, the peak position of these fitted 2 states varies within like 20 keV. So gated on these 2 states, we can get the cross sections of these 2 states and compare to the DWBA calculations from Terry Fulton. We can, using the Vincent Fulton technology, we can see that both states agree quite well with the L equals 1 angular momentum transfer. This limited the possibility of spin parity to 0 minus, 1 minus, and 2 minus. But it's worth noting that for this 3.2 MeV states, the L equals 0 can't be fully excluded from this figure. But if this is L equals 0 transition, then these states will decay via emission of 1 L equals 0 neutron. Because this won't encounter any central barrier, the final decay-wise of these states can be quite large, which is not agree with the experiment. So these 2 states, as I show you here, have a dominant branching ratio to a beryllium 11 plus 1 neutron. So in order to look at the coupling to continuum effect and included in the calculation, Smith Wang carry out this gamma of couple channel approach calculation for beryllium 12 system. And in his calculation, the beryllium 10 is a deformed core. He used the Wood-Saxon universal potential to represent the interaction between the valence neutron between the valence neutron and the core. And you can find more detail of the interactions in this paper. So here we also compare the result with the shell model calculation. You can see that compared to the shell model calculation, the result from the gamma of couple channel approach strongly reduces some of the excited the excitation energy of some of the excited states, and especially for these weak bonding states or resonances. So and our result of our experimentally observed 2 states seems to agree with their calculation of the 0 minus states for the 3.2 MeV states and 1 minus or 2 minus states for this 4.4 MeV states. So The question is why there are so much difference between the shell model and the gamma coupled channel approach. So possibly because the shell model uses the harmonic basis. So this in this case the nuclear behave like a closed quantum system. So the coupling to continuum effect or the big bonding effect won't be included in this calculation, in this kind of shell model calculation. But in the gamma coupled channel approach, more realistic potential has been used for the valence neutron and the core, and the coupling to continuum effect can be included in this calculation. So this effectively reduced some excitation energy of some states, especially for the weak bonding and unbound states. This is similar to the reduction of the single particle energy of the low I value states approaching the threshold, which has been observed in many systems and has been used to explain many phenomena. So here I also show you the two neutron density distribution within the Jacobi coordinate in the gamma coupled channel approach. So you can see here, the ground state is a mixture of dineutron structure and Siegel-like structure. And for these two states, the 1 minus and the 0 minus states, the two valence neutron are less correlated. So and for the 2 minus states, there is a small enhancement in the dineutron structure. And for the second 1 minus and 2 minus states, I didn't show the distribution here because they have a very large decay wise, which exist even exceed their excitation energies. So these two states are threshold resonances. Possibly because they have a very dominant configuration with involve the S1/2 orbital. So this component won't encounter any central barrier, so it's strongly impacted by the coupling to continuum effect. Now I come to the final part of the talk. I will show you some new science opportunities with the real accelerated beam coupled to ATTPC and Solaris. So Solaris will be coupled to the future facility of IFRIB at the real accelerated beam line, and it will realize the full potential of the science opportunities possible with the real accelerated beam at around 5 to 20 MeV per nuclear. And Solaris in the silicon mode is quite similar to the design of Helios, but with the silicon array at both upstream and downstream of the target. So we can also put the ATTPC into the magnetic field of Solaris. This will give more advantage for the detection of ATTPC, which I will show you in the next slides. So the ATTPC is a large gas field detector. The nuclei in the gas volume act as the target isotopes as well as the tracking media, which give a very large effective luminosity. So it will allow the direct reaction to be carried out with beam as weak as 100 particles per second. So the ATTPC can get more advantages when operating with the magnetic field. So where longer trajectory can be recorded. Here I show you one example of the charged particle within the ATTPC. you can see that the charged particles were bound by the magnetic field while slowing down in the gas of ATTBC. And also, the ATTBC opened a possible way of proton-iodine reactions, which is not accessible with normal solid target. So during the transition period from NICL to IFRIB, there are some opportunities with long-lived beam. So we plan to carry out some measurement during this transition period. So here I show you there has been some debating about if there is a proton density deflection in the silicon, or it will result in the change of the spin orbital splitting. So some studies show that this change in the spin orbital splitting is resulted from the weak bonding effect. So it is still remain an open question whether the sudden change, whether there is a sudden change of spin orbital splitting, which might link to the appearance of the deflection in the central proton density. So we will study the spin orbital splitting in the n=19 isotopic chain and determine if there is a sudden change of the spin orbital splitting. So we plan to carry out this measurement during this transition period using Solaris. And here I show you the shell model predicted states to be populated in the silicon-32 DP reaction. So here I also show you the weak bonding effect for the spin orbital splitting as the green arrow. You can see that the excitation energy of the single particle strength of the P1/2 play a crucial role in determining this trend and if there is a sudden change. So we can, with this reaction, we can also probe the L=3 spin orbital splitting by using the excitation energy difference between the 5½ and 7½ states. So we also want to commission the ATTBC using one-nucleon transfer reactions on the long-lived beam of beryllium-10. So because there has been many sites of measurements with this reaction, so we can compare our result with the previous result to test the capability and the resolution of the ATTBC for transfer reactions. And with this measurement, we can also confirm the spin parity of the 3.4 MeV states, which is not has not been confirmed yet. So we can also compare our result with the calculation within the framework of nuclear field theory in this paper. And this will unify the structure and reactions for our work. So here I show you some examples of the simulated trajectories from the beryllium-10 DP reaction and the beryllium-10 DT and DD reactions within the ATTBC with the magnetic field. So here I come to the summary of this the present talk. I show in this talk I showed you some overreaching questions of nuclear physics. These include the evolution of the shell structure and how what's the the original of this change in this shell structure, and transfer reaction is a powerful experimental tool to study the nuclear single particle structure. And I show you using beryllium-11 negative parity states how the one-nucleon transfer reactions can be used to approach the different theories for the nuclear, and how we compare our result with the different theoretical models. And using the beryllium-12 low-lying zero plus states, I show you how we determine the cross-shell configuration mixing within these two states, and how the lowering of the d5 half orbital was shown in beryllium-12. And also, I show you how the coupling to continuum effect can influence the excitation energy of the unbound states of beryllium-12. In the final part, I show you some new science opportunities with the real accelerated beam coupled to ATBC and Solaris. So here are the collaborators for the work I present in this talk. Thank you very much. So questions or comments are very welcome. Thank you.